Okay, hi everybody. So prove the Babylonian square root sequence converges to squiggly line 2. Okay. So first, recall. Okay, well, maybe I'll say proof. Recall, dear reader, that xn plus 1 is equal to the average of xn and 2 divided by xn. Okay, that was recall that is the recursive definition. DEFN is my abbreviation of definition. Okay. Now what? So first, we will show the limit exists in the real numbers, right? Remember, the real numbers are the place where all Cauchy sequences converge. Where all Cauchy sequences converge. And the real numbers are where we have the monotone convergence theorem, where the monotone convergence theorem applies. And if you remember the proof of the monotone convergence theorem, it exactly involves showing that the sequence is Cauchy. Okay. So first we'll show the limit exists. Then once we know it exists, we'll show it's equal to the square root of 2. Then, when we're sure it exists, we will show it equals square root of 2. Okay, so how do we do the MCT? To show the limit exists, well, we need to show monotone and bounded. We need monotone and bounded. Okay, so let's experiment. First of all, what we should notice is that this is an average. The next term is produced by averaging two numbers, this number and this number. The AM-GM inequality, the arithmetic mean, geometric mean inequality, says that, what does it say? I think that the average of two numbers, I think is greater than or equal to the geometric average, which is their multiplication. And this is provided that both numbers are positive. So the x and y, provided x is positive and y is positive. Okay. So let's just apply this. We have this side is, becomes 1/2 xn plus 2 over xn. Should be greater than or equal to xn times 2 over xn. Okay. You see what I did here? I just sort of pattern matched. This is a really good inequality to remember. So anytime you see an average, try this inequality out. Anytime you see something like this, try the inequality out the other way. I don't know what the other way is. There's only one way, but there's two sides to the inequality. Now, what is this equal to? Well, square root of 2. Interesting. What is this equal to? Well, that's the next one. Xn plus 1. Okay, so we have shown this proves what? What does this prove? This proves that every xm except possibly the first one, the whatever we plug in to get started will be greater than or equal to the square root of 2. In other words, square root of 2 is a lower bound on everything except the first number. So let's just see that. Like if we start this at x at 1, if we plug in 1 here, what will we get? Then the next one will be 1/2, 1 plus 2 over 1, which is 3/2. And 3/2 is about 1.5, which is greater than or equal to the square root of 2, which is like 1.4 something. And so even though 1 was, 1 failed to be greater than or equal to 1.4, the next one, as soon as we plug this in and get the next value, that will be bigger than or equal to the square root of 2. And you can see, we proved that, but let's just test it out. Let's try 1/10. If we plug 1/10 in, so 1/10 obviously fails. It's strictly less than the square root of 2. But the next one will be bigger than the square root of 2. So let's try it. We take 1/2 times 1/10 plus 2 over 1/10. That's 200 tenths. So this is 20, and then I want to add, so I put it over a common denominator. And so you see that what we're going to get is 201 tenths, which is 201 20ths, which is basically 10. And 10 is bigger than square root of 2. So what we're finding is that square root of 2 is a lower bound on everything except the first number. And the first number doesn't matter for convergence, okay? The bound. The first number doesn't matter for convergence. Doesn't matter for convergence. Just throw away the first number and start at the second number, okay? So if you really insist, and I guess the problem does, if the problem insists that we start at 1, let's just throw that away and say, look, let's start at 3/2. Because when you plug in 1, you get 3/2. And 3/2 is, in fact, bigger than or equal to square root of 2. And so square root of 2 is a lower bound. And we've shown that the next one will always be greater than or equal to square root of 2. Okay. So we have lower bound. That means we have bounded. Okay. Now, let's do the next one. Let's do monotone. So if we're bounded from below, here's square root of 2, and maybe here's 3/2. And what we'd like to prove is that we're going to march downward. So we want to show monotone decreasing. Okay? So what's the definition? We need to show that the next one is smaller than the previous one. The next is smaller than the previous. That is decreasing. Okay? And then once we've shown that, now we have decreasing bounded below, and that means the monotone convergence theorem applies and the limit exists, and we're done with the first part. Okay, so let's just see what happens. Well, we know what this is. This is 1/2 xn plus 2 over xn by definition. So the first inequality is true if and only if this inequality is true. Let's multiply by 2. Let's multiply the entire thing by xn. And here we're going to use that xn is positive. So this only works for xn for positive numbers. Otherwise, actually, I think we would converge to minus the square root of 2. But anyway, let's just get positive the square root of 2. So we'll assume that these are positive. Because then we can multiply both sides and the inequality stays the same. If you multiply both sides by a negative number, the inequality would switch. So it's important that x of n is positive. The inequality stays the same. We get 2xn squared, xn squared plus 2. I multiplied by xn. Okay, 2 less than or equal to. xn squared. Okay, I don't know why that took me. I just subtracted this from both sides. And great. Interesting. What does this mean? It means that if somehow we knew that square root of 2 is always less than or equal to Rxn, this is equivalent to having monotone decreasing. But oh my goodness, we actually know this. This we already proved. So the if and only if chain means that we have. So we now proved monotone decreasing. Okay, so now we've got monotone and bounded, therefore, so now the monotone convergence theorem applies and the limit exists. Call that limit W. Okay, we're just going to give it a name. In other words, this sequence limits to W, or we could say the limit of the x sub n equals W, or we could just, say that this limit, I don't know. These are just two different ways. Now, here's the thing. Apply the limit laws to the recursive equation. So remember what the recursive equation was. It's that the next one is equal to the average of these two things. So let's apply the limit laws to this entire equation. What we get is the left-hand side times the limit of the right-hand side. Now, we said, what's this? In fact, this is W. So if you just, the limit of a sequence, if you just re-index the sequence, if you just shift the sequence by 1, it doesn't affect the limit. So we actually get a W for this right-hand side, for this left part. This is W. And now here we'll have a limit, the limit laws from section 2.5 of our book. That means that we can take this limit inside to, through a fraction, through addition, through multiplication, the basic operations of adding and dividing and multiplying by half, it all just passes through, and we get this. By the limit laws. Okay, so this is W and this is W. We have a name for that limit. And now let's just manipulate this equation. Let's multiply both sides by 2. This looks very similar to what we had before. Let's multiply everything by W. And let's subtract W squared. And we see that W is square root of 2 since W is positive. Since all the x sub n are positive. Why do we know they're positive? Well, they wouldn't be if we started somewhere else. So if we plugged in -1, then the next one wouldn't be positive. But provided we plug in something positive, then we can apply the AMGM inequality and show that the next thing will be bigger than square root of 2, and so the next thing is positive. So as long as we plug in a positive thing to start with, the AMGM inequality ensures that everything else is positive. Since all the xn are positive, if we plug in a positive number to start. So we're done. That's awesome. We finally did it. We We applied limit laws. We used recursive equation. We used the arithmetic geometric mean inequality. We showed that something is monotone decreasing and that it's bounded, that it has a lower bound and it's decreasing. So the picture sort of looks like this. Wow, this is a good one. This is a good one to really understand. Take your time, really understand this. And probably the best way is to try it yourself with a blank sheet. Can you prove this?